Hi everybody, welcome to week 10, the final week of Math 121. You're almost at that finish line. Today we are going to cover our final topic in the course. The final topic is conic sections. So we'll cover 8.7 and 8.8. 8.7 covers circles and parabolas. Now, if you look on page 641 of your textbook at figure 8.27, you'll see some really nice diagrams, far better than what I could ever draw up here on the whiteboard. Page 641. What those diagrams show, in each of them you see a double cone. It's a cone like standing on its self. Two cones standing point to point. Now, if you can visualize a plane slicing through those cones in different ways, you can come up with a parabola, a circle, an ellipse, and a hyperbola. Now, as part of your homework, I've assigned an animation in MML, and that shows you at least how circles work in the plane. But I've also, in the announcement for today's class, I've also assigned a web page for you to go to that has really good diagrams of these four conic sections. So the simplest one to cover is the circle, and that's one that we're already familiar with, that and the parabola. The general form that all these conic sections take is this. There's an x squared term, an xy term, or liable to be these terms, a y squared term, an x term, a y term, and then a constant term. So you see the coefficients that were chosen here, capital A, B, C, D, E, F. Everything is set equal to 0. Everything's cleared to one side, which is usually how we set up a general form of an equation. But before we can talk about circles or any of these, we have to talk about the distance formula. This is on page 642 of your textbook. Suppose you had 2 points, x1, y1, and x2, y2 in the plane, and you wanted to measure that distance connecting them, that line segment connecting them. Let's call that distance d. Now, what else can we observe here? Let me polish up my diagram a little bit. Well, if we were to imagine a horizontal dashed line going across here, it hits the y-axis at that number there, y1, right, the y-coordinate of that point. If we imagine another horizontal line going across, it hits the y-axis at y2, which is, of course, the y-coordinate of this point. Now let's visualize some vertical dashed lines. This one goes down here. It hits the x-axis at x1. In other words, the x-coordinate of this point. The x-coordinate of this point is x2, so a vertical line going downwards would have to hit the x-axis at x2. So the question becomes that point right there. If I think about this right triangle, and I've put in the right angle symbol right here, this makes a right triangle right there. What are the coordinates of that point? Well, that is its y-coordinate, right? It has the same y-coordinate as that point. And it's going to have the same x-coordinate as that point. Furthermore, and I'm going to change colors here so things don't look so cluttered and get harder to read. What is the distance from here to here? In other words, what's this side of the right triangle? Well, distance is always non-negative, so we better use absolute value bars. And it's this y level here, right, y2, minus this y level, which is y1. So it's y2 minus y1, right? Everybody agree that's the distance to get from here to here? By similar reasoning, the distance from this point to this point, in other words, this side of my right triangle, is x2 minus x1, and I wrote it as absolute value. Now in this case, the way I've drawn this triangle here in the first quadrant, where all the numbers are positive, I didn't even need the absolute value bars. However, if we were to take this diagram here and rewrite it in the second quadrant, third quadrant, fourth quadrant, where we'd have some negative coordinates, we'd need these absolute value bars to keep everything true and making sense. So how are we going to calculate D? Well, let's go back to something we saw earlier, the Pythagorean theorem. Again, this was figured out about 2,500 years ago by Pythagoras. And that's only appropriate because, as your textbook mentions in the introductory paragraph, conic sections were actually known by the Greeks 2,500 years ago, or 2,000 something years ago. The Greeks were actually aware that these different shapes could be found by intersecting planes with cones in three-dimensional space. So that's pretty good for a long time ago. They really figured out something amazing. Well, okay. We know that this is true. C equals a squared plus b squared when you have a right triangle like this. All right, well, in this case, we called the hypotenuse of the right triangle D. So my distance squared is going to be equal to this side squared plus this side squared. I'll write it in this order with the x coordinates first. Okay, so we're just applying the Pythagorean theorem. This number here, absolute value of x2 minus x1, is playing the role of A. This number plays the role of B. All right, well, since we're squaring, those absolute value bars that I was so careful to put in there, I don't need them, as it turns out. Because this difference here is getting squared. Same thing for the y coordinates. So now I have a formula that tells me what distance squared is. I'll just take the square root of each side. And there it is. That is the distance formula. And that's a really essential formula. You can't do too much more mathematics than you've done already without using this from time to time. This is going to pop up all the time. Okay, so how does this relate to circles, our first conic section? Well, we know the definition of a circle is all points equidistant from a center. So here's a diagram. If I pick some point in the plane, call it C, and say, okay, that'll be the center of my circle. Then if I draw all the points that are distance r from that center, I get a circle. All right, so that's the geometric definition of a circle. How about if we put it in a Cartesian coordinate system? All right, we'll give the points coordinates so we can measure exactly where they are. Let me switch back to black ink. Look at figure 8.29. Here is a circle whose center is right at the origin. And the radius of the circle is 3. So if that's 3, then the circle goes through there. This would be -3. The circle would go through there. Here's 3 on the y-axis, so the circle goes through there. And -3 on the y-axis. So the circle looks roughly like that. Very roughly. Okay. Now, if we look at any point, boy, that's so bad, I'm just going to have to redraw that. It's really tough to draw circles and stuff like that on these little whiteboards. Okay. If we look at any point x, y on a circle, this distance is the radius of the circle, and we know that it's 3. All right, so what have we figured out here? D is 3. So, if I plug this into the distance formula, and I'll plug it into this higher up form, the distance squared formula, I'm going to get this. 3 squared equals x minus 0, right? Because the other point that we're measuring the distance to is the point 0, 0. So I have distance squared equals x coordinate here minus the x coordinate there squared plus y minus the y coordinate squared. And of course the y coordinate is also 0. 3 squared is 9. This is just x squared. This is just y squared. So what I have is the equation of the circle whose center is at the origin and has radius 3. That's pretty good, but what you'd really like to do is talk about the circle that has center anywhere in the plane. So, let's look at figure 830 on page 643. Suppose we think about the circle whose center is at -2 and 3, and this circle has radius 4. A picture of it is in that figure there. -2 is over here, +3 is over here, so there's the center of the circle. Now, the radius is 4, so it's going to stick out to about here maybe, and I'll draw the circle. Again, my apologies, it's really tough to draw those things on a whiteboard like this. So, what have we figured out? The radius squared is going to be equal to x, if we call this point xy, this is any random point on the circle, and of course the center, as we said, is -2, 3. So that radius squared is going to be equal to any point minus its coordinates, respective coordinates squared and summed up. Right? So everybody agrees I'm using this formula to just make a statement as to how the distance from the center to the circle must be equal to this for any point xy that you find on the circle. If I simplify this algebraically, I get 16 equals x plus 2 quantity squared plus y minus 3 quantity squared. And that shows me something. It shows me that the standard form for a circle is always going to be this. It's always going to be, if the center is HK, then the circle will always be x minus h quantity squared plus y minus k. Notice it's minus, minus, not added. Y minus k quantity squared equals the radius squared. So that is standard form for a circle. Well, go ahead and do problems 2 and 6 on page 647 in your textbook. In number 2, it says, write the equation of the circle with center at 2, 5 and radius square root of 5, and graph the circle. Then number 6, the instructions for that group of problems says, find the radius and center of a circle with the given equation. So just look at that equation in 6. Tell me what's the radius and tell me what's the center. And we'll be back in a minute.